In a universe of seemingly infinite scale and countless wonders, it's curious that the one thing we're desperate to find is something as ordinary as ourselves, to discover that we're not alone. Just 40 light years away, in the constellation of Aquarius, lies a tiny, dim star, TRAPPIST-1e. It's cold, ancient, and barely visible. And yet it hosts something extraordinary. Not one, but 7 Earth-sized planets. It's as if nature itself set up an experiment. Can life exist around a star like this? One by one, scientists have ruled out most of these worlds as being habitable. Too hot, too cold, no atmosphere, no chance. But one world still holds promise. TRAPPIST-1e. And now, thanks to data from the James Webb Space Telescope, we may finally have a glimpse of its atmosphere. What we found is astonishing. Could this be the first true Earth-like planet beyond our solar system? Could TRAPPIST-1e host life? I'm Alex McColgan and you're watching Astrum. Join me today as we travel to the TRAPPIST-1 star system to explore the potential for life on its most promising planet. We'll look at new data from the James Webb Space Telescope that has pushed it to its limits, revealing the likely composition of TRAPPIST-1e's atmosphere and whether it could support life. That is, if the very star that offers the chance of life hasn't also issued a death sentence. TRAPPIST-1 is an M8 class red dwarf. Only a little larger than Jupiter, it's 1,800 times less luminous than our Sun, a difference that's like comparing a candle to a college running track floodlight. Although the star was first discovered in 1999, its full planetary lineup wasn't revealed until 2017, when it became the first and only planetary system to be discovered by the TRAPPIST Optical Robotic Telescope. This telescope is made up of 2 parts, TRAPPIST South in the Chilean mountains and TRAPPIST North in Morocco's Atlas Mountains. They use transit photometry, a technique that measures periodic changes in the brightness of a star to find orbiting planets. In other words, if a planet passes between us and the star, then some of its light is blocked, and so we detect a dip in the star's apparent output. By taking multiple observations, the telescopes were able to isolate the individual orbits of multiple planets around TRAPPIST-1. Initially, their data analysis only found the 3 innermost planets, but further data from both of the TRAPPIST telescopes, as well as the Spitzer infrared space telescope, took this total to 7. And not only that, but they are all rocky, and all, at least roughly, Earth-sized, making this the most Earth-like planets found around any star. If you'd like to know more about all the individual planets around TRAPPIST-1, I made a video about them. You can check it out with the link on screen. But with such a small, dim star at the center, is there really any hope that they could be habitable? For any of these planets to receive enough light to support life, the orbits need to be much closer than we are to our Sun. In the TRAPPIST-1 system, the planets certainly are. In fact, all 7 are incredibly close. TRAPPIST-1e orbits only 1/13 of Mercury's orbit, which means it could be tidally locked to its host star, the same side of the planet facing the star at all times, just like we only ever see one side of our own moon. This has significant implications for the habitability of the planet, and we'll dive into those later in the video. But more interestingly, its orbital distance also means that it is right in the middle of the predicted habitable zone, where it receives about 2/3 of the energy that we do from our sun. And that is why scientists are so curious about this planet. But it takes more than light for life to thrive. TRAPPIST-1e would almost certainly need an atmosphere, so that's exactly what scientists have been looking for using our most powerful space-based telescope, James Webb. The teams who were involved with developing James Webb were rewarded with guaranteed observation time. One group, the deep reconnaissance of exoplanet atmospheres through multi-instrument spectroscopy, that's right, the DREAMS team, immediately wanted to set James Webb's sights on the TRAPPIST-1 system. The James Webb Space Telescope is uniquely sensitive and precise, so much so that it can detect spectral signatures from the thin band of gas that makes up the atmospheres of these planets, a whole 40 light years from our own. It does this thanks to a technique called transmission spectroscopy. As an exoplanet passes its mother star, James Webb not only measures the drop in brightness, but also how the spectrum of light changes. The telescope's near-infrared spectrometer, or NIRSpec for short, measures the wavelengths of infrared radiation closest to the visible spectrum. Molecular bonds absorb energy in this range, and different bonds, like this carbon-hydrogen bond in methane, or this carbon-oxygen double bond in carbon dioxide, absorb different wavelengths. It means that by measuring which wavelengths are absorbed as a planet transits its star, we can first of all work out if there is an atmosphere, and then, if so, determine which gases are present. And it's been particularly easy to get a read at TRAPPIST-1. In fact, the data we have is 10 times more sensitive than what we have on any other system. Why? Counterintuitively, it's because the star is relatively dim. The light a planet obscures causes a bigger relative drop in apparent brightness of this star than the same planet passing in front of a large, bright star. A bigger difference is easier to measure. Using these measurements, the team have already discounted TRAPPIST-1c and d from having atmospheres, but results from observations of TRAPPIST-1e, a rocky planet around 0.9 times the size of Earth, were so intriguing that scientists couldn't ignore them. It looked like this planet may, in fact, have an atmosphere, and that was more than enough evidence for the DREAMS team to decide to use up all their guaranteed James Webb time trying to find more. So far, they've seen 4 TRAPPIST-1e transits with James Webb. But what did they find? Well, we can start by discounting a few possibilities. We now know that TRAPPIST-1e does not have a primordial atmosphere, one a planet is born with. These are usually dominated by light gases like helium and hydrogen, which haven't been detected. They were likely stripped away by the star's radiation early on in its life. Nor does it seem to have a carbon dioxide dominant atmosphere like Venus, which is thick and dense. An atmosphere like that of Mars, which is thin and sparse, is also unlikely given the recent measurements. Believe it or not, all of this is good news, as it's unlikely that any of these atmospheres could support life. Well, not as we know it anyway. So what atmosphere does it have? Well, here's the big one. There could be an Earth-like atmosphere, one dominated by a heavier gas such as nitrogen, with a strong greenhouse effect from water, carbon dioxide, or methane. Such an atmosphere with a surface pressure of around 1 bar, equivalent to Earth's, may be able to sustain enough heat transfer to the dark side of the planet to allow a global surface ocean, despite it being tidally locked. Were this confirmed, that would make headlines the world over. However, that might be too much to ask. The data instead slightly favors the idea that TRAPPIST-1e is a cold planet without a global ocean. Analyzing the data correctly here is key. Being able to understand what we're seeing and what it means is the difference between the discovery of the century and an embarrassing mistake. But if you're a scientist tasked with data analysis, don't worry, you can brush up your skills with Brilliant, the sponsor of today's video. Brilliant is an online learning platform for beginners and experienced learners alike. It's home to thousands of visual, interactive courses designed by an award-winning team of teachers, researchers, and professionals from Stanford, MIT, Caltech, Microsoft, Google, and more. It's quite the star-studded lineup. I love its courses on science. But there's also topics about programming, mathematics, or AI, so you'll have every tool you need to evaluate promising exoplanets or tackle things a little closer to home. You'll start off with the foundations, but will soon see yourself taking on increasingly challenging problems as you improve your skills and understanding. To learn for free on Brilliant, click on the link brilliant.org/astrum in the description below, or scan my QR code. My viewers get 20% off if they want to subscribe to Premium, so be sure to check it out. It's a great way to support the channel. Let's get back to TRAPPIST-1e. As I mentioned, there is an alternative to an Earth-like atmosphere. High levels of methane instead create a reverse greenhouse effect. TRAPPIST-1 has a surface temperature of about 2400 Kelvin, much cooler than our Sun's 5670 Kelvin, and more of the energy it outputs is shifted to the near-infrared wavelengths. Atmospheric methane can absorb that energy before it even reaches the surface of the planet, then re-emit it into space, resulting in a cooler atmosphere. For the tidally locked TRAPPIST-1e, this would mean that liquid water may only exist on the surface of the planet that permanently faces the star. No global ocean here. But that's not necessarily bad news for life either. Such conditions could satisfy Darwin's warm little pond hypothesis of the origin of life, and atmospheric modeling has backed this up. Simulations suggest that even if TRAPPIST-1e has limited water, or if what water there is locked on the dark side of the planet, it could still have a stable atmosphere. Although, this may lead to what's known as terminator habitability, where life could only find a home across a dynamic band in perpetual twilight that separates day from night. But water on the surface isn't the only option. We know TRAPPIST-1e is rocky, but not much more than that. It may be an icy volcanic planet with a subsurface ocean, like we find on Europa and Enceladus in our own solar system. Life on Earth is believed by some to have formed near deep sea vents, and the same process could happen on 1e. No matter where on TRAPPIST-1e water may be, life is possible. There's an energy source and potentially an atmosphere that provides the building blocks for life. But there is one issue. Although all these things are possible, scientists can't completely rule out the possibility that TRAPPIST-1e is a cold, barren, and airless marble with no atmosphere at all. So we need to talk about what could prevent a stable atmosphere from ever forming. And in this case, it's the red dwarf star TRAPPIST-1 itself. Imagine standing with me on TRAPPIST-1e just for a second. Look up. The star above us would appear more than 4 times as large as our sun in the sky. The star would be a deep red-orange color, illuminating the sky as if it were in perpetual sunset. What a sight that would be. Now, red dwarfs are extremely active, and they produce more powerful flares than our Sun, and more often too. The worst recorded geomagnetic storm to ever hit Earth was the Carrington event in 1859, a greater than 1 in 100 year event. TRAPPIST-1 is believed to release a flare this powerful more than once every 2 days. You'd likely be able to watch solar flares arcing out into space in real time. And they carry huge amounts of energy towards a planet, enough that over time any atmosphere could be stripped away, making life as we know it all but impossible. That's assuming that the atmosphere was ever allowed to form at all. Red dwarfs are stupendously long-lived. TRAPPIST-1 is expected to exist for 10 trillion more years. That is 700 times the current age of the universe. By comparison, our Sun likely only has 5 billion years left before it becomes a red giant. You might think, given the stability and lifespan of a red dwarf, there would be plenty of time for life to find a way, but because of their long lives, their chaotic and energetic teenage years before red dwarf stars settle down are correspondingly longer. It's during these formative years that some planets begin to produce their own atmosphere, slowly replacing their primordial hydrogen-helium atmosphere with one comprised of heavier molecular gases such as carbon dioxide, nitrogen, and methane. These chemicals are released from inside the planet through volcanic activity. The problem is, if the aggressive atmosphere stripping phase of a star lasts too long, then an Earth-sized planet might not have enough resources within its interior to fully generate a stable, life-supporting secondary atmosphere. The unfortunate reality is that if a planet's atmosphere isn't established before 5 billion years, it may never generate one, condemning the planet to a death sentence before it was ever allowed to live. I know it's actually sounding rather hopeless for TRAPPIST-1e, and I bet you're wondering, how is this one of the most promising planets? But we don't yet know one way or the other whether an atmosphere has survived or not. We've already seen there are hints of its existence, and although the star's violent outbursts may be 1e's downfall, they may also be completely necessary for life to begin. UV radiation from flares may be essential to create RNA building blocks, molecules that are central to the metabolism of every life form ever found. And now that TRAPPIST-1 is in its calmer main sequence phase, with lower UV and X-ray irradiation than in its juvenile past, there is a chance of a stable, habitable atmosphere existing on TRAPPIST-1e. And that atmosphere could have protection from the continuing flares with its own magnetic field, just like the Earth does. The Earth's magnetic field exists because its outer core is a moving mass of molten iron and nickel. There is a good chance that TRAPPIST-1e has a similar system. In fact, TRAPPIST-1e's close orbit to the red dwarf could actually help maintain its magnetic field. If TRAPPIST-1e's orbit is eccentric, this would cause repeated compression and relaxation of the planet's shape. This process creates internal friction that could heat the interior as much as 0.18 watts per meter squared. That's roughly 24 times the tidal heating flux generated in the Earth. We see a similar process in Jupiter's moon, Io. Io is tidally locked with an eccentric orbit and gets stretched and squashed by the gravitational interactions with the other Jovian moons, pumping it full of energy and making it the most volcanically active body in the solar system. So, where does this leave us? Well, we may have an Earth-sized, volcanically active, rocky planet with the building blocks for life, its own atmosphere and magnetic field, orbiting in the habitable zone of a relatively calm red dwarf. Or it could be a cold, dead world. So, let us know in the comments which you think will eventually be confirmed. We might not get an answer until the proposed Habitable Worlds Observatory, a telescope designed to look for life around stars like our own, which launches in 2041. But until then, James Webb's observations are our best bet. The fact we are able to measure the light absorbed by a thin gaseous layer around a rocky planet orbiting a dim red dwarf star 40 light years away is pretty incredible. And scientists haven't given up hope. They've learned from the first sets of James Webb data and modified their technique to achieve more precise measurements. With another 15 transit observations planned before December, they expect to be able to confirm the presence or absence of carbon dioxide and a secondary atmosphere, a key step in the search for life on 1e. Perhaps TRAPPIST-1e and its neighbours will turn out to have a unique, inhospitable atmosphere, or perhaps one that could theoretically support life. Or maybe, just maybe, we'll find one just like home. It's exciting to find so much potential for life relatively nearby, even in the midst of an extreme environment. But whatever the atmosphere turns out to be on TRAPPIST-1e, with the recent discovery of formations on Mars that are thought to have been impossible to form without life, I find it hard to shake the feeling that the discovery of extraterrestrial life feels inevitable. The only question is, when? Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrom content. I'll see you next time.